Okay, so in this video, we're going to grasp the concept of continuity. Continuity. And we're doing continuity because it is one of the important applications of limits. And now that we know how to evaluate a lot of limits, we can start continuity. So continuity is basically, it means the same thing as you would expect it to mean. It's continuous. A function is continuous if it doesn't break, if it doesn't jump, if it's smooth and connecting. So let's look at an example of a continuous function. So this is continuous. It doesn't really break. Okay, it's our function f. Now, there are three conditions at which a function is not continuous. Okay? So there's condition A. Okay, so I'm going to draw three versions of a function g. So a function's not continuous at a point if a function's not defined there. So if there's a hole or if it's like a vertical asymptote, then it will not be defined there. So on an interval, it's not continuous. It breaks. It's not defined. So f of x is not defined. How about this graph, this version of g? So this is g of x, sorry. So what about g of x? Well, if you're concerned about this interval, well, another way g of x cannot be continuous if the function g of x is defined at that point, but the limit itself is not. So we've talked about whether a limit exists. Here, the limit, let's call this c. The limit as x approaches c of g of x does not exist. Okay? So there's a third type of a function that's not continuous. Okay, so this is our interval. So the function can have a limit at c and is defined at c, but the limit, okay, this is our point c. The limit as x approaches c of g of x does not equal to g of c. So the value that this approaches does not equal the actual value of the function. So that's also an example of a discontinuity, the opposite of continuity. So which means there are three conditions that you have to follow in order for a function to be continuous on a point. Okay, so first, the function is defined at c. So 1, f of x is defined at c. So no holes at c, no vertical asymptotes. Okay, so f of x is defined at c. So there's another condition. The limit that as x approaches c of f of x actually exists. Okay? And the third case is that the actual limit as x approaches c, now that we know it exists, it has to actually equal the value of the function. And if all these are true, that means you know that the function will be continuous at a point. You can also have continuity on an open interval. So these are the intervals I was talking about here. Okay? This span of x values, that's an interval. So to be continuous on an interval, that means every point on that interval should also be continuous. There should be no holes or vertical asymptotes, anywhere between the 2 points. Okay, so let's do some example functions. Okay, so I'm gonna just get rid of all of this. Delete. So let's look at the graph of f of x equals 1 over x. Okay, so if you were to graph it, what would it look like? Well, on an open interval, so these are continuities at open intervals. I say open because it's important. If you had it on a closed interval, then you would have to see that the function exists at the closed interval. So let's just focus on this for now. I'm going to see where it's continuous here. So you could clearly see that the function is not continuous everywhere. Okay? Why? Because you have this vertical asymptote. A vertical asymptote is like a line that a function approaches as x gets closer and closer to a value. So you can see the limit as x approaches 0 of f of x does not exist. And f of 0 is not defined. So this is not continuous. However, if you were to look at every other point, there seems to be no breaks. No breaks. That means it's continuous from negative infinity to 0 or 0 to infinity. So these are the two intervals. Okay, negative infinity to 0 and 0 to infinity. Okay, so these are the two intervals that it is continuous at. How about this? G of x equals x squared minus 4 over x minus 2. So how do you graph this? First, you can factor it out. You can factor something out. X plus 2, x minus 2 over this. So let's just factor it out. So you have x plus 2. However, there is a condition, x cannot equal to 2. Why? Because it would make the original function undefined. So it would look like this. It would look like this. This, except with a little hole up here. Which means it's continuous from negative infinity to 2 because g of 2 is not defined. So it's not continuous at 2, but it's continuous everywhere, at every place other than 2. So you might be wondering, how can we do this without a graph? Okay, how can we do this without a graph? Well, let's look at a problem. Okay, so let's look at a problem. Select all, delete. So let's have a function, f of x. So this is a piecewise function. This is a piecewise function. So you have the negative x plus 3 if x is less than or equal to 0, and 1/2 x plus 3 if x is greater than 0. So first we need to check whether the limit exists. Okay? So we have to see whether the limit exists. The function definitely exists since we know these are continuous everywhere. We just need to check if it's 0 to see if it's continuous on the whole line. Okay? So we want to see, is this continuous? Is f continuous at x equals 0? So that's the question. So we know f of x is defined at 0. F of 0 is defined. Since we have a condition for x equals 0, that's just the top function. So f of 0 is defined. So that's good. So our second test is to see if the limit exists. So let's take the limit as x approaches 0 from the left. Well, as x approaches 0 from the left, well, everything to the left of 0 is defined by this top function. So the limit as x approaches 0 from the left, that's how you check if the limit exists. If the limit from the left equals the limit from the right. Okay, so from the left, it is negative 0, which is 0, plus 3, which equals 3. Okay, so that's the limit from the left. How about the limit to the right? The limit to the right, well, it will start coming down the bottom function. Okay, the points to the right of 0 will all be on the bottom function, since all the numbers greater than 0 follow the bottom function. So let's substitute 0 into the bottom function. So that's 1/2 times 0 plus 3. So 1/2 times 0 is 0 plus 3 equals 3. Okay, so since the limit from the left and the limit from the right both equal to the same value, the limit as x approaches 0 of f of x exists and is equal to 3. So it exists. Our final condition is the limit equal to f of 0? Because remember that one instance, the limit exists, the function was defined, but the function was defined at a different value than the limit. So first we have to find f of 0. F of 0 is equal to negative 0, or just that's just 0 plus 3 equals 3. So f of 0 is 3, the limit is also 3. That means the limit as x approaches 0 of f of x equals f of 0. So equal to 3, which means it's continuous. It's continuous. Which means it's continuous on the whole line, because both of these functions don't have any breaks in them. The only doubtful point we have was 0, because that's where the functions change. So let's do another type of problem. We're going to find the x values where f is not continuous. And before we start this problem, there's a second part. Which of these are removable? So before we start, let's talk about what removable means. So when you have a whole, okay, if you were to actually define g at the whole, you would remove discontinuity. So let's just draw a sample function. So this is g. G is not defined at c. However, if you were to define a new function that is identical to g but is defined at c, you would remove the discontinuity. Okay, you would remove it. So if you were to define it at c, it would be removed. It would be continuous. So that's why wholes, okay, the wholes especially like this, with like a hole, those are known as removable. Non-removable does not care whether a function gets redefined. So that happens at things like jumps. So even if you were to define at this point, it would still not matter because the limit itself does not exist. So this is non-removable. This is removable. And another case would be a vertical asymptote, something that approaches infinity or negative infinity. Because the function just will never be defined at 0. Will never be defined. And the limit's not defined either. So that will be non-removable. So let's look at f of x equals x plus 2 over x squared minus 3x minus 10. So we have x plus 2, we're going to factor the bottom. So that's x plus 2 times x minus 5. Cancel, cancel. So we have 1 over x minus 5. So let's analyze this. So since we canceled 2, we know there'll be a whole at negative 2. So there'll be a whole at negative 2. So one of our x values is definitely negative 2. We have another, now we have to check the domain. Where is the function not defined at f of x? Where is at which x value is f of x undefined? Well, set the denominator equal to 0 and you get x is equal to 5. It's a negative 2 and 5. Which of these are removable? Well, you have a vertical asymptote at x equals 5, since that makes it 1 over 0. Which means that will be non-removable. However, negative 2 is a whole. Okay, if you were to define it at negative 2, then it would no longer be a whole. It would remove the discontinuity at x equals negative 2. So x equals negative 2 is removable. Okay, let's do one more. Okay, let's do one more. We're going to do this one. Okay, so we are going to find let's have a function f of x. It's a piecewise function. Okay? So we're going to find a constant a. So this x cubed is defined as x cubed when x is less than or equal to 2, and as ax squared with x greater than 2. So we're trying to find the constant a so that the function is continuous on the real line. Well, both of these functions do not have any breaks naturally. So the only thing we need to consider is x equals 2, whether the function will be continuous at x equals 2. Because at everywhere else, they will not have a break. This is a cubic, this is a quadratic function. So you know they'll not have any holes or asymptotes. So let's try to figure this one out. First, we need f of 2 to exist. So f of 2 has to exist. So f of 2 exists because, and it's 8. 2 cubed is 8. We use the top function. So f of 2 is 8. What is the limit as x approaches 2 from the left? The limit as x approaches 2 from the left is equal to, since there's no rearrangement necessary, you just do direct substitution. That's 8. So we're almost done. We need to find in order for it to be continuous, this has to be equal to the limit as x approaches 2 from the right. From the right of ax squared, which means this has to be equal to 8. Remember, this is a quadratic function. So you could use direct substitution because there is no whole in a quadratic function, in just a pure quadratic function. So a times 2 squared equals 8, or 4a equals 8, or a equals 2. So a has to be equal to 2. Okay, and that makes sense. F of the limit as x approaches 2 from the right is 2 times 2 squared is 4, times 2 is 8. That's equal to the limit, which is also equal to the function, which means it's continuous if a is equal to 2. And we are done.